Welcome students to this first lecture on some preliminaries which we need to know. So essentially this I am supposing that we know, and I am just giving you the basic facts. Okay, so first of all we need to know what a vector space is, right? And of course I am assuming that we know, but still it's just a revision that you are looking at a set, of course a non-empty set. So V, you have a non-empty set, right? And this set, we will put some operations on it. So first of all, this non-empty set with a binary operation, okay, binary operation, which we will call addition, and then we'll also have a binary function on it, okay, and a binary function on it, which we will call as scalar multiplication. So the set along with these two operation and a binary function, and it has to satisfy certain assumptions, and it satisfies certain assumptions, satisfies the below assumptions. So what are the assumptions? Okay, so first of all, associativity is there. So what is this? It is basically U plus V plus W. You can actually write it as U plus V plus W. Okay, that is associativity. Okay, right. Now this is associativity of vector addition. Okay, now we have something called a commutativity. Commutativity is this: U plus V will be V plus U. This is commutative VT, okay, of vector addition, okay. And then we'll have an identity element, which we are basically going to call it as a 0. So identity element is 0, and what is the property? So there exists an element 0, we'll call it a 0, okay, in V, and we'll call it a 0, such that V plus 0 equals to 0 plus V, yes, and this is equals to V. This should hold for all V in the vectors, in the sets V, right? So if you take any element of the set, if you add 0 with it, doesn't really matter in which way you are adding, these always yield you a 0. This is the identity element, okay, identity element. And then of course you have the inverse, right? Inverse with respect to addition, vector addition. So for every element V in V, okay, you will have, there exists minus V in V, such that V plus of minus V, so plus is always given to you, right? So that is going to give you the identity element 0, okay. So that is the inverse. So if you have a element V, you always have a inverse minus V, right? Now so these are the 4 properties which addition, so with respect to addition it should satisfy. And then the other properties which we need is the scalar multiplication, right? So A times BV should look like AB times V. And what is AB here? A and B is in R, or whatever field you are choosing. For this course, we are always going to choose the set over R, right? So that is your scalar. So here I am saying scalar multiplication. It means the elements which we are multiplying with the vectors will be from element V. So the scalars will come from R, okay. It can come from C also, but for this course at least now we will always consider it to be R, okay. So the scalar field is R, and then you have this property that A times BV. So BV is an element of V, right? So when you multiply it by A, it means that AB times V, okay. And then you have this property that identity element with respect to the scalar multiplication, right? So 1 times V is equals to V, okay. So this is the multiplicative identity, actually multiplicative identity, okay. And then you also have distributive property. Distributive property is A times U plus V is A times U plus A times V. So this is distributive. Distributive. Okay, and then you also have distributivity of scalar multiplication with respect to the addition. So that will be given by A plus B times V is A times V plus B times V. Okay, so essentially here you see I am assuming A to be in R and UV is in V. Okay, R can be in any field F, you can replace it with there. And again here AB is in R and V is in V for any V in V. Right? Doesn't really matter which one. This is also distributivity, but this is distributivity of scalar multiplication with respect to the field addition. Okay, so these are the properties, and this as I'm assuming you already know this stuff. Okay, so let's move on to the next part. So essentially what we have is, let's look at some examples which we can build out of this. Okay, so we always know that the first example which we can consider is example A is of course R, right? So R over R. So I am choosing V to be R, the real number, real, and then the field which we are choosing is of course R. Then R over R. This is a vector space. Vector space, right? And okay, so another one, of course, you have V. Let's say you have Rn. So this is Rn over R. Okay, that is also a vector space. This is also a vector space, and we call it a real vector space because it is over R. Okay, so Rn over R, that you can do. And of course, so these are the preliminary vector spaces which you already know. I'm assuming that. And of course, there is another vector space which is very important in our context, which is Pn of R. What is Pn of R? So this is the set of all those polynomials. What are the polynomials? So basically you are looking at this thing, a0 plus a1 of x plus an of x power n, right? And here a0 an, these I am choosing it from R, right? So this is a polynomial over R, that is the coefficients are basically chosen over R, and this is all possible polynomials of order less than equal n. Okay, so so this is basically polynomials of order less than equal n. Okay, and with this you can of course see that this is also a vector space, is a vector space. Okay, and once you have this, we can also talk about what is the dimension of all these spaces, right? So what is the definition of dimension? Let's just go over this quickly. Dimension of a vector space. So we will define the number of linearly independent elements. So this is the minimum number. Okay, the minimum, let's just say, put it this way, the minimum number of linearly independent elements required to span V. Okay, so what does this mean? Let's understand this. First of all, what is linearly independent elements? Okay, so linearly independence, first of all, we have to understand this, right? Linearly independent. What is it? So essentially, you are basically looking at a subset of V, right? So given a vector space V, you are looking at a subset. So what is the subset? Let's just call it S. And the subset is given by some elements of V. Let's just write it like this: V1, V2, Vn. Okay, be a subset of V. Clear? Now we call Vi, the set is linearly independent. Linearly independent. When is it? Then if you look at this relation, so that is C1 times V1 plus Cn times Vn equals to 0. This will always imply that every C1, every Ci, that is C1 equals to C2 equals to C3 equals to Cn, this has to be 0. So essentially, as an example, you can of course think of it that they do not depend on each other. So essentially, if you just think of two elements V1 and V2, so as an example, let's just look at it. You see, if V1 and V2 are linearly independent, what does it mean? Linearly independent. If I say something like this, that will imply V1, C1 times V1 plus C2 times V2 equals to 0 cannot be written as V1 equals to C2 by C1 times V2, right? You can't write it like this. You can't write it like this because for linearly independence, you have C2 and C1 both has to be 0. So this division is not possible. Okay. So what does that mean? It means that one vector should not be a scalar multiple of another. And what does that mean? It means that let's say V1 and V2 are vectors. So if you think, if one thinks that they are vectors in Rn, right? Vectors in R2, let's say. In R2, let's say. So V1 and V2 are vectors in R2, let's just say. So V1 is not a scalar multiple of V2. It means that they are not parallel to each other, right? So if they are parallel to each other, it means that they are scalar multiples, and in that case V1 and V2 are linearly dependent. So if they are parallel, they are linearly dependent, and in this case, since you can see that one cannot be linearly dependent of another, then they are not parallel to each other, right? So that's your linear independent. And now the thing is the minimum number of, so what is the dimension of vector space? This is the definition which we are going to use. We are going to use the minimum number of linearly independent elements required to span V, right? Okay. So what does that mean? It means that what is span of V? So let's just define that also. Span of V. Okay, so one thing I must say, you see, I am skipping most of these concepts because I know that all of you know this thing. Okay, I'm just telling you the basics in case you have forgot or something. Okay, so what is span of V? Span of V is this. So basically, given any element, let's say V in V. Okay, so what happens is you can actually have a set. Okay, so let's say S is the set. This S, let's just say this S which I defined here. This S spans V if any element V can be written as summation Ci Vi. Is it okay? So basically I equals to 1 to M. Doesn't matter what M is. M is some N. So basically you can take some elements of this set, and after that you can combine them to form any element of this initial set V, and then we call that S spans V. Okay, and it doesn't have to be linearly independent. You see, it can be more than that. Okay, it doesn't really matter. But the thing is, what it means is basically, if you are given some elements, with the help of those elements, you can linearly combine those elements to produce any element of your original space V. Okay, that's your span. Okay, so and if you have the minimum number of element which is required to span V, then we call that as the dimension of a vector space. So for example, let's say the dimension of R, as you know, is 1. Okay, why? Because any element, let's say R in R can be written as R equals to R times 1, right? Okay, so what is your basis element here? So what is the set which actually spans R? The set will only contain 1. Okay, so the basis set, okay, let's just call it S, that will only contain the element 1. Okay, and then again, let's say what is the dimension of Rn in that case? Dimension of Rn, of course, it is n, right? And what is the basis element? Basis, let's call that basis element S. See, what happens is, let's just try to find out what is the basis. Huh? Okay, so any element, let's say V is in Rn, can be written as V equals to V1 1 0 0 plus V2 0 1 0 plus Vn 0 0 1. Okay, so the nth element is 1. So here V, if the coordinate of V is given by V1 V2 Vn, we can write it like this, right? V can be written like this. So basically, you see, if I denote these things 1 0 0 as E1, so let's just denote it as E1, this as E2, this as En, then this is nothing but summation Vi Ei, right? And then you can see that, and please prove this, huh? So please check this part, check that there cannot be n minus 1 linearly independent number of elements which can span V, right? Okay, so essentially what is the basis element here? Basis contains E1 E2 En. Once you prove this, and then the dimension will be n. Okay, right. So similarly you can check, so please check this part, that the dimension of Pn of R is going to be n plus 1. And why is that? Because you can see that the basis element, let's just call the basis element, this set as so basically it will contain this element 1 x square and x power n. You see this element, all of this, if you combine it together, this will actually produce, first of all you have to show this is linearly independent, and then you can, once you show that, you can show that this can actually span any element of this set. So there basically you can show that this is going to be the basis of Pn of R, right? And this is very important for us. Okay, so why it is important? Okay, so here this is the first example which I think is going to be a little different than what you have known till now about vector spaces. So D, an example of vector space. Okay, so first of all I will start with the interval I. Let's just call it as AB. So in most of this course, whenever I am saying I is an interval, just think of it as a closed bounded set AB. So this is a closed bounded set, closed and bounded interval, right? Interval in R. And of course you guys know that this is nothing but a compact set in R, right? Compact set in R. Okay, right. Now we define, okay, you define CAB. What is CAB? CAB we define it as the set of all continuous functions, okay, continuous functions in AB. So the function is defined on AB, okay, and then we call those as CAB. So basically you take all those functions together and you form a set. This is called CAB. Now this I can actually show that this is going to be a vector space, okay. And what is the addition and the multiplication? So basically what I mean is this, see, if you start with two elements F and G in CAB, right? If you start with two elements, then F plus G, the addition, okay, will be defined it like this. See, this X is from I, right? Okay, so F plus G times X, we can define it like this, F of X plus G of X. Okay, you can check that this operation actually satisfies all the properties of vector space. So that is your first one, and the second one is C times F. If you want to define it, so you can define it like this, C times F of X. Okay, so please check this part, check that these two operations on CAB forms a vector space. Vector space over R. Okay, over R. Why? Because here C is in R and F is in CAB. You do realize that, you see, I am saying this is a vector, right? CAB is a set of all continuous functions on AB. Okay, you see, I'm saying that any element of this set is a vector. Okay, so these are actually functions, continuous functions, right? But we are calling them as vectors. Okay, since this actually satisfies all the properties of a vector space, so we can call them as vectors, right? Okay, now one important thing is this. See, okay, okay, what are the examples? Let's look at some examples of CAB, some elements of CAB. So of course, if you define let's say f1 of x to be exponential functions, exponentials, right? Exponential x, or any functions which is like the proper trigonometric functions, so sines, cosines, let's say sin x. Okay, so that can also be element of this set. And then of course you also have the polynomials, right? So let's just write it like c0 plus c1x plus cn x power n, right? X is x is in from CAB, x is in AB, and Ci is from R, right? So this is a polynomial. Any polynomial that will also be a continuous function. So if you do not know this, please, what you can do is please check this part. Check that f1, f2 and f3 belongs to CAB. Okay, right. So this forms a vector space. Very nice. Okay, right. Now the thing is this. That's the vector space. Good. Now can we talk about the basis of this? Basis of CAB. Basis of CAB. Okay. So what is the basis of CAB? See, CAB is a very different set than all of this, whatever I have defined, R, Rn, Pn of R. Why? Because the thing is, this is an example of an infinite dimensional vector space. Okay, so basis of CAB, what is the basis? This is the question. So basically, what the dimension, we can say dimension of CAB is infinite. Okay, so this question is out of the context for this course, but basically what I'm trying to say is, what does it mean? It means that there does not exist, okay, so sorry, let me just put it, there does not exist any finite subset, okay, subset of CAB which is linearly independent. Okay, linearly independent, let's just call it LI, linearly independent. This is how I'm going to write in this course, okay, because it saves time and I don't want to write so much. So LI, okay. So basically what it means is, you cannot get a finite subset of CAB. Okay, so you cannot get a finite collection of continuous functions which are linearly independent and which spans CAB, okay. So what I mean by this, vaguely speaking, or not very mathematically speaking, intuitionally it means that if you cannot have a finite collection of continuous functions defined on closed interval AB such that you can span any element of CAB with those, right? Finite combinations of what I mean. Okay, so and how do you prove such a thing? So this, please, you have to do this part yourself. So you check this. See, can you give me a subset of CAB? So first of all, any subset of CAB, you can think of it as Pn of R is a subset of CAB, right? Is a subset of CAB for any n in n, right? So it doesn't really matter, all polynomials, okay, it doesn't really matter if it's the first order polynomial, second order polynomial, nth order polynomial, whatever it is, they are all continuous functions. Sorry, I have to write it like this: Pn of r defined on AB. Okay, so defined on AB. Okay, so basically any polynomials defined on closed interval AB, okay, that is always contained in CAB, right? That you can of course see, because any polynomials are continuous functions. Okay, now, so, and since this works for any n in n, okay, doesn't really matter what n is, so you can see that of course the dimension of CAB is going to be infinite. It cannot be possibly finite. Okay, so but the thing is, this is not a precise way of putting it. I mean, this is just an intuition. Okay, and please, I want you to do that. You just show that the dimension of CAB is infinite. Okay, now what sort of infinite? Countable, uncountable, we don't know that. We don't need to know that right now, but the thing is, you just need to know that the basis is the number of elements on the basis is infinite, right? Okay, right. Now, can we produce more vector spaces out of it? Of course we can. Okay, so we define this. So we define CKAB. What is CKAB? CKAB is the set of all k continuously differentiable function on AB. Okay, right. So you can define it. So basically what I am doing is, what do I mean by continuously differentiable? So first of all, as an example, let's say, what is C1 of AB? It means we are looking for a function f, okay, from AB to R, such that the function is continuous. Okay, f is continuous. Okay, see, Ck is kth continuously differentiable function, right? So up till kth order. So basically it is like so C1 is up till first order. Okay, continuously differentiable. So it means that f is continuous, f prime exists, and is continuous. Right, so that is what it means, that the first derivative also exists and it is going to be continuous. We call it a C1. So similarly, C2 also you can think of it as the second derivative. So f is continuous, f prime exists, f prime will be continuous, and then f double prime will exist, and f double prime has to be continuous, and then you have C1 of AB. Yeah, and as you can see, I mean, you can guess that this CK of AB, these sets are always going to be infinite dimensional. So this also you need to check, that CK of AB is infinite dimensional. Okay, right. So this is basically the ideas of vector spaces which you are going to need. Okay, now another question I want to pose here, and I want you to understand this, that is there any inclusion between all these spaces, CKs? Okay, so essentially what I mean is this: you see, you can actually see that CAB is the biggest space, right? So basically what I mean is, let's say C1 of AB and CAB. What is the relation between these? See, if a function is continuously differentiable, once continuously differentiable, it means it is going to be continuous, right? So the continuous function space is actually bigger, right? So C1 of AB is contained in, so let me put it this way, CK of AB is contained in, sorry, CK plus 1 of AB is contained in CK of AB for any k equals to 0, 1, 2, right? Okay, and similarly you can see that, right? Because if it is, if the k derivative exists and it is going to be continuous, then k minus 1 derivative also exists and it is continuous. So basically one is included in another, right? And we can also define this. You can also define C infinity of AB. C infinity of AB, and this we will define in our course. For our course, I will define it to be the intersection of K equals to 0 to infinity. Sorry, this is intersection of all Cn's, okay, Cn of AB. Okay, so n is in n essentially, n union 0. Okay, so basically what I'm trying to say is this: you take all Ck's and you take the intersection of that, that will give you C infinity. So this we will call it as a set of smooth functions. Okay, so with this we are going to conclude the lecture, but before I do that, just a quick question. There exist elements in CAB which are not in C1 of AB. Okay, yeah, and one small details also which I missed, and I should add that part also, that see here, this I am using all this inclusion as a part of subset. Okay, but you can also define something called a subspace, right? This you already know, but still let me just do it. Subspace. So basically you have a set V1 subset of V. Okay, so given a vector space V, this is given. Okay, V1 is called a subspace if, and this is the easy way of doing it, that given V1 and V2 in V1, okay, so okay, maybe I should write it like this one second. Let me put it this way: V and W in V1 will imply V plus W is in V1, and C times V in V1, V in V1 and C in R will imply, right, C times V is in V1. Okay, so if these two properties are there, so of course if it is V in V1, V and W is in V1, it has to be in also in V. But basically what I'm trying to say is this: the V1 inherits the properties of the scalar multiplication and the vector addition. Those two operations, those two binary operations, the properties are inherited by V1 also, and then we call it a vector. So V1 will form is also a vector space. Also a vector space, right? Also a vector space, and then we call it a vector subspace of V. Is also a vector space over whatever the field is. Let's say here the original field is in R, right? Vector subspace over R, and we call it a vector subspace, okay, of V. Yeah, and as an example, of course, you can see that let's say C1 of AB is a vector subspace of CAB, right? It's a vector subspace. Okay, so this is a subspace. Okay, and of course you can also see that, let's say, this space define V1 to be this space. C infinity, okay, so you don't have to write C1. So let's just define C infinity of AB. That is also a subspace of CAB. Okay, now one question, and this is where we are going to end the lecture. One question is this: can you find a finite dimensional subspace of CAB? Okay, so that is the question, and with this question